So 4/5 equals tan inverse t over 2. How do I solve that for t? So tan inverse, is this the same thing as saying tangent of 4/5 equals t over 2? Is that the same thing? Yes. Okay, so tan inverse, inverse tangent is how we find an angle, essentially. So this is saying tangent of the angle 4/5 equals t over 2. Okay, so for this one, I would just multiply both sides by 2. And when I work all this out, I end up with t equaling, where's my notes? T ends up being, I end up with t equaling 2.059. So that's a time, and that's 2.059 days. So it takes 2.059 days for the colony to reach a mass of 6 grams. Again, that's not the final answer. They're saying, what is the instantaneous rate of change of the mass at the moment that it reaches a mass of 6 grams? So now we do want to find P prime of 2.059. And this one's kind of messy because we have inverse tangent. We know we have to take the derivative of that function, but this is a with calculator problem. So let's let the calculator do the heavy lifting on this one. So, oops. So everybody take out your calculator. Let's do a quick refresher on this. How our calculator, because remember our calculator can evaluate a derivative at a point. We have a point of 2.059 and we have a function, so let's let the calculator do the derivative, evaluate it at that all in one step. So start a new document, unsave the unsaved changes, say no. All right, so let's just start from a fresh screen. So we press menu, we go to option 4 for calculus, and for me it's option 2, derivative at a point. I'm just going to use my variable, I'm just going to leave it as x. I know it's t's in my function, so I just have to make sure I replace that. And my value is what I just found there, so that 2.059. Hit OK. So again, it's going to evaluate my derivative at 2.059. So now I put in the original function that they gave me. And so the original function they gave me is 2 plus 5. And then with your calculator, whenever you're doing trig functions with a multiple in front of it, literally write it out as 5 times tan inverse. Because if you just write 5 tan inverse, it doesn't like that. So explicitly say I'm taking 5 times my tan inverse, and ours is x over 2. Hit enter, and you end up with 1.21. So again, let the calculator do the heavy lifting. The calculator in the background, it's finding the derivative and inputting your value of 2.059. So we go back to our problem here. Our answer was 1.213669, and so it would be letter C is the one that is correct. And you can see there's no 2.059 anyway, so that work that we did to find T, even if you got confused and you stopped there, that's not correct anyway, because there's not going to be an option choice for that one. So the correct one on this is 1.214. So this is all stuff we can do, but this is kind of a little bit different order than what we've been doing it in. So pay attention to units, read through the problem, make sure it makes sense. Do you understand what is being asked and what steps you have to go? Layla. Yeah. Okay. Any questions on this problem? All right. I'm going to go on to question number 2. I'm not obviously doing them all. I'm just picking a couple of them. Just happen to be 2 in a row. So this one says, the derivative of the function a is given by a prime 2 plus 9e 0.04 sine of t. A of 1.2 is 7.5. If the linear approximation to a of t at t equals 1.2 is used to estimate the function a of t. So they're giving us a derivative, but they're asking us about the original function a of t. So again, we have to use that linearization formula. So a of t linearly approximated is a of 1.2 plus a prime of 1.2 times t minus 1.2. Again, linear approximation, you need to make sure you know that formula. Okay, a of 1.2, they tell me, is 7.5, so there's nothing I need to do with that. A prime of 1.2 I can calculate because they give me my a prime formula. So a prime of 1.2 is 2 plus 9e 0.4 times the sine of 1.2. Work that all out, I end up with 15.06635. So this is plus 15.06635. And then t minus 1.2. The question asked is, at what value of t does the linear approximation estimate that a of t equals 15? So now I'm going to have my a of t is 15, so 15 equals 7.5 plus 15.06635 t minus 1.2. And we need to solve for t. So this is just a refresher on that linear approximation, that you need to know that linear approximation formula and be able to fill in from the context of the problem what pieces you know and what pieces you're trying to figure out. Okay, I'm going to jump to question number 6. So number 6 is a particle motion problem. So these ones, velocity, acceleration, these ones are going to be fair game for the test on Wednesday. All right, the AP test in May is cumulative, and this is an AP progress check. So they are checking to make sure that you are up to speed up to this point in the year, that you know this material. So just because we haven't seen any particle motion problems for a few weeks doesn't mean we're done with it. Doesn't mean it's gone to be forgotten. We're going to keep recycling this stuff through so that we don't forget about it. Says a particle moves along the x-axis so that at time t greater than 0, its position is given by x of t is 2t cubed plus 3t squared minus 36t plus 50. What is the total distance traveled? So traveled, we're talking about movement. X of t is simply a position. So at this time it's here, at this time it's here. Well, if we're actually talking about movements, we need to find velocity. So that's the first derivative. So 6t squared plus 6t minus 36 is that first derivative. So let's look at movement on this first derivative. Brady. Okay. All right, so this is the velocity function. So now we're working with movement. Let's figure out when our movement is 0, because velocity can be positive or negative, moving left, moving right. And so this one, if I were to figure out where this is equal to 0, I could factor out a 6. So this is t squared plus t minus 6. I could factor this to be t plus 3 and then t minus 2. So it equals 0 when t is negative 3 and t is a positive 2. Again, t, though, is equal to time, and they give us the interval that the time has to be between 0 and 5. So we don't even have to worry about the negative 3, because that's outside of our interval. We can't have a negative time anyway. So we know when time, so 2 is a critical point. So if I made a quick sign chart, I know at time t equals 2, it's 0, so it's not moving. But let's look what's happening before it, and let's look what's happening after 2 seconds. So if I were to just test a point, let's say 0, time t equals 0, because that's in my interval. If I put 0 back into my function up here, so I'd have 6 times 3, 18. 18 times a negative 2 would be a negative 18. So this is negative. So I know it's moving left from 0 to 2. Number greater than 2, if I chose 3, I'm going to end up with a positive value. So this is saying after 2 seconds, it's moving to the right or in the positive direction. They want to know the total distance traveled. It doesn't matter if I'm going left or I'm going right. What is my distance that I'm traveling? My total distance, not my net distance. And we'll talk more about this as we get further on into the next integral calculus stuff. They want to know total distance. If I went 5 miles left and then I go 5 miles right, I actually went 10 miles. It's not that I went 0. I actually went 10 miles. That's my total distance. So to actually figure out that movement, we're going to go back to the original x of t function, because I want to now think of distance. How much did I move? Well, I'm going to use absolute value because I don't care if I went 5 miles left and I'm thinking that's negative. I'm not worried about the negatives. So I know I'm going to go from x of 2 minus x of 0. That's going to represent this first interval here. And you could have done x of 0 minus x of 2. It doesn't matter. Plus my next interval, which is x of 5 minus x of 2. All right, so that's giving me my distance, how much I've traveled. So this first interval, I went 44 units. It would have been negative 44, but I'm not worried about the negative. And then my second interval was 189 units. So work all this out. I went 233 units. That's my distance of travel. That's this particle's distance of travel. Again, the negative, disregard the negative, put in absolute value bars, or just disregard it in your mind, however you got to do it. But that total distance traveled, we figure out when our velocity stops, when we have a velocity of 0, but then we're going back into the original position function to give that distance. So it's kind of like a y2 minus y1 type setup. Okay. All right. I'm just going to get you started on this number 7. I'm going to do a couple more even after this. So number 7, another particle movement one, moves along the y-axis at time t is greater than or equal to 0. Its position is given by this, y of t over the interval from 0 to 4, what values of t is the speed of the particle increasing? How does speed relate to velocity, Brady? Correct. So remember, speed is the absolute value of velocity. So I don't care if my velocity is positive or negative. So speed is simply the absolute value of velocity. Now, in terms of rate of change, so this is the position function. If I looked at the first derivative, so my velocity, if I saw my velocity was positive and my acceleration was positive, could I say my speed is increasing or decreasing? So if I have a negative velocity and it's getting more and more negative, my speed is increasing. Oops, I told you that wrong, but I said negative to negative because that works also. If the first derivative is negative and the second derivative is negative, it's still increasing. Okay, because my velocity is going down, but it's going down in a faster rate. So if the signs are the same, it's increasing. If the signs are opposite, so the first derivative was negative, and we'll say the second derivative is positive, that means the speed is decreasing. Or if my first derivative was positive and my second derivative was negative, again, that's decreasing. So for speed, and we did touch on this a few weeks ago when we were talking about particle motion, if first and second derivative have the same sign, it's increasing. It could be positive or it could be negative. As long as they're the same, it's increasing. If they're different signs, the speed is decreasing. And you will need to know that for the AP test in May. So this is a very common type question, but it'll ask you a question about speed. You got to look at first derivative and second derivative. Okay, so for this one, you need to find y prime and y double prime to figure out which intervals, because they want to know strictly where it's increasing. So you want to figure out where your y prime and y double prime are the same sign. Okay, question 14. This might be difficult to read back there. Let's see if I can zoom in a little bit. Zoom in a little bit there. 14 says the locally linear approximation of the differential function f at x equaling 2 is used to approximate the value of f of 2.3. The approximation at x of 2.3 is an underestimate of the corresponding function value of x at 2.3. Which of the following could be the graph of f? So again, they're asking us about saying it's an underestimate. So that's the key word here, that it's an underestimate. Local linearization, remember, was that L of A, or well, it's L of X. L of X equals f of A plus f prime of A times x minus A. So we're working with a derivative, working with a slope of a tangent line. If we look at A, whoa, go back. If we look at A, I can see my slope, my tangent line here would be right here on this black line. It'd be the exact same. Okay, so it wouldn't even be an estimate, it'd be exact. If I look at B and I drew a tangent line here, it's going to come above my curve. And so if I went out to 2.3, I'm actually above my curve. And so that would actually be an overestimate. Make sense? If I look at C, I drew a tangent line here. And I go out to 2.3, I would be above my curve. So again, that's an overestimate. If I went on this one and I drew my tangent line, I go out to 2.3, I'm below the curve, that would be the underestimate. So on this one, concave up will actually prove to be an underestimate. Concave down will be an overestimate. So this one is letter D for number 14. But there's a lot of almost duplicate wording that they got going on in the setup to this problem that, there's a lot, for me anyway, there's a lot to kind of sift through. Okay, this is really all they're asking me about. But that understanding the idea, okay, my tangent line, I can create an under or an overestimate. A was actually right on. Two more. Number 16. Which of the following limits does not yield an indeterminate form? So stuff with limits again. What was the indeterminate form when we were working with limits? Anybody remember what that was?
0.
Good. Okay. So if you end up with 0 over 0, what would you do? I heard it. Yep. I heard it over here first. Okay. So 0 over 0 is an indeterminate form. Also infinity over infinity or negative infinity over negative infinity. So those are all indeterminate forms. If you end up with an indeterminate form, you cannot evaluate the limit. You need to use L'Hopital's rule. So this one just says, which of the following does not yield an indeterminate form? So if I looked at the first one, the limit as x approaches 0, well, my numerator would go to 0. By denominator, I'd have 0 minus sine of 0. Sine of 0 is 0. So this goes to 0. So this one does not work because that does yield an indeterminate form. And remember, I said never write 0 over 0, infinity or negative infinity or infinity, because really those are 1. So if you wrote this equals 0 over 0, that's false because you're saying the limit equals 1. The limit does not equal 1. Okay, so this one does create an indeterminate form. So if we actually wanted to solve the limit on this one, we'd use L'Hopital's rule. We'd evaluate the derivative of the top, evaluate the derivative of the bottom, then try and take the limit as x approaches 0. Okay, but they're not asking us to do all that. They're just saying which one does not yield an indeterminate form. A does yield an indeterminate form, so therefore that's not the right answer. B says as x approaches 2, so it's the natural log of 2 over 2, which is the natural log of 1. The natural log of 1 is saying e to what power equals 1? 0. So this one, the top goes to 0. I have a bad habit of doing that. The bottom, I would have 4 minus 10. 4 minus 10 would be a negative 6 plus 6. That goes to 0. So this one does not work. C says x approaches pi. In the numerator, I have pi minus pi, so my numerator goes to 0. The bottom, I have cosine of pi. Cosine of pi is actually negative 1. So C is the true solution, the correct solution for this one, because that does not yield an indeterminate form. And D, as I go to infinity, this one does create an indeterminate form. I end up with infinity over infinity for this one. So there was a refresher on L'Hopital's rule in indeterminate forms. Last problem. All right, so I'll zoom in on this one a little bit so you can see a little bit better. The figure above, and this is 18, this is the last problem that you'll have too. The figure above shows the graph of the twice differentiable function g and the line tangent to the graph of g at the point 0, 3. They're saying the value of this limit is what? Okay, so this is, come on. This is the limit as x approaches 0. The function is g of x times e to the negative x minus 3 all over x squared minus 2x. So if I were to do a direct substitution in here, What is g of 0 for my graph? Might not be able to see it very well in the back. 3. What's e to the 0? 1 minus 3. Oh, I can already see the top starting to go to 0. The bottom, I'd end up with 0 squared minus 0. So the bottom's going to 0. So I have an indeterminate form. So that means I have to use L'Hopital's rule to continue on. All right, so my limit as x approaches 0 still. Now I have to find the derivative of the numerator. So g of x times e to the negative x minus 3. What is the derivative of g of x times e to the negative x? Use product rule. I think I heard that. So what's the derivative of g of x? G prime of x. Okay, good. We're getting better with this. Okay, and then this would stay. Plus g of x would stay. What's the derivative of e to the negative x? Negative e to the negative x. Negative e to the negative x. Because it'd be e to the negative x times negative 1. So this would be times negative e to the negative x. And the derivative of 3, or the negative 3, we don't have to worry about. The denominator would be 2x minus 2. All right. Now with substitution, what is g prime of 0? 2. Who said that? How do you know that, Leah? Correct. Why is it doing this? We'll get back to it. I don't know why it won't let me zoom in. But, so g prime of 0 would be the slope of the tangent line here at 0, which is this diagonal line. So we can find the slope of that line if I chose like this point right here. So I rose 2 over 1. So g prime of 0 is 2. And so I have 2 times e to the 0 is what? 1. Minus g of 0, which is 3, times negative e to the negative 0, which is what? Negative 1. Okay, because it'd be e to the 0, which is 1, but then we have that negative going on. So it's a negative 1. And these actually should be plus between those two. 2 times 1 plus 3 times negative 1, all over negative 2. So 2 minus 3 would be a negative 1 divided by negative 2, which is a positive 1/2. So letter B would be correct. But I want to do this one again to don't be intimidated when they have a function in there that you're doing the derivative of. It actually makes it easier. Derivative of g of x is g prime of x. And you can continue on. So you'll notice you might notice I jumped from question 7 to question 14 on here. There's like 5 related rate problems in there for you to work on. We're good enough now. I didn't need to set you up on those. You guys are good on those. Okay? So for the remainder of the day, continue working on this. Finish them up tonight. We'll talk about them tomorrow at the start of class. And then we will look at a couple more. And then we'll test on Wednesday. You hate what? I'm sorry. Believe it or not, I'm doing this for your benefit. This is for your own good. Listen to your dad. This is for your own good.
You're my dad now?
No, it was a quote. In quotes. Because I said so. There you go. Is that more accurate? If you need somebody to talk to when you're doing homework at 1 a.m., send Brady a text. He'll be up.
we need anybody to talk to while doing homework at 1 a.m. You will go.
Right?